Okay, so at the end of class yesterday, I said that system, that ordinary differential equation has as a solution any function of the form y equals k e to the minus x over 2. So if I take the derivative, plug it in, it works, regardless of what the constant k is. Now, let's consider a different differential equation. And yes, I've deliberately picked one that is not linear. That square root of y blows me out of the water. But I actually do have a solution for this. You should check. Let's make sure that works. Y prime is right, because when I do it with the chain rule, I get 2 times all of this junk to the 1, and then the derivative of the inside is going to be, sorry, 1/4 times 2x. Well, wait a minute, 2. So I get an x 1/4 x squared plus c to the first. Well, wait a minute, this expression is the square root of this one, isn't it? So this is x square root y, exactly like I wanted. It satisfies our differential equation. But this is a one parameter family, right? I have choice of c here. The reason we don't allow for c being negative is because I've got the square root of y over there, and then I could have a negative under the square root, and that's not allowed. So I'm not going to do that. I just want c bigger than or equal to 0. But there's another solution that's not written in this form. There's actually a really easy solution, a trivial solution. The equation y equals 0. What's the derivative of 0? 0. 0 equals x times the square root of 0 works. That's an exception. So it's another solution, but it's not part of our family. That's called a singular solution. As opposed to the parameter family of solutions. Sometimes there are multiple singular solutions. Sometimes there are different families. Depending on the complexity of the problem, we could end up with a one parameter family and one singular solution, or multiple different singular solutions, or we could end up with 2 separate families or more. Questions? It is also possible that if we have We had an example like this on Monday as well. I don't remember what I'd actually written down for the pieces, but I had partial with X and partial with Y. Well, wait, no, these aren't partials. This is a system of differential equations. What's a solution to this? Well, a solution to a system is going to be multiple functions. So a solution here is going to look like two functions. And each of those functions will have an interval. Mia, just like we were asking at the beginning, I need an interval to be defined for each function. But that means the interval for my system's solution has got to be made up of the overlap between those two intervals. So let's say that our first function was defined for all positive values of x. And then our second function was only defined for values of x less than 10. Then the only place this system would work is between 0 and 10. We need both of them to work to satisfy our system. Now, again, smaller systems, two equations, relatively easy to solve. Larger systems, not so much. But in order to make that work best, I want to rig the game. Then I want to go to how I do simultaneous equations in other places. Oh, right. Matrices. I'll go back to linear algebra. So that officially ends section 1. I ran just short, realized I needed to cover those pieces. Questions? Frequently, I need more than just a general solution. And in a sense, our families, our one parameter families, are general solutions. I want to be a little more particular. So let me go back to Calc 1. Here is a differential equation. A Calc 1 differential equation. Here's f prime of x. What's f? Good.
Okay. X to the fifth minus x to the third plus 4x and plus.
And that's absolutely correct. But this is a one parameter family. There are infinite many answers here. So now I'm going to ask you the same question I asked in Calc 1. What's C? We have no idea. The difference between a general solution to a differential equation and a particular solution is having initial values. In Calc 1, that typically looked like I gave you a little bit of extra information. So here's an initial value. At the point x equals -1, the y value is 2. What does that give me? I got something else. A negative to an odd power is negative. Which means I get a particular equation. So not only does this function satisfy my differential equation, it also satisfies my initial value. So I can actually say what I really solved is the initial value problem, as opposed to just solving my differential equation. So again, I'm digging back into my calc class. We did a problem where you threw a ball off the side of a cliff, and then like a second later you threw another one, and they figure out if they cross. Or long time ago, man. Calc 1 was a long time ago. If you go back and look at the calc book, you'll find that problem. But in order to solve the problem completely, we actually had two constants we had to solve for, because what we had was only the second derivative. We had gravity, right? Gravity is negative 4.9 meters per second squared. That's all I know. Great. You throw the ball up at 10 meters per second. You know how tall you are, how high you are up in the air. Okay, wait a minute. I have multiple initial conditions. In general, here's an nth order differential equation. Now I've written it with the highest derivative isolated, our standard form. But I'm going to add the initial conditions. And notice I have an initial condition at the same x value, x0, for every one of the derivatives here in the right-hand side. These are my initial conditions. If we think of the Calc 1 example, we did this, we got a one parameter family. We then used a value to nail down a single function. Back in Calc 1, I said, oh, when we write down this equation, what we're really creating is a bunch of parallel graphs. And then this is a point, -1, comma 2. So that one, that's the one we want. Well, here, I'm going to have n minus, well, n different parameters, right? 0, 1, 2 to n minus 1 is a total of n conditions here. So I have n parameters to solve for, and then I go, oh, this is the one I want. It's not just one of these possible curves, it's this specific one. Here is a differential equation. I hope the following is not a question you will find difficult. Here's one thing. Give me an equation that solves this. What's a function whose derivative is equal to the original function? 0, absolutely. Give me a non-trivial one. Function, you take the derivative and nothing changes. E to the x, right? And if I use any multiple of that, right? Y equals c e to the x. When I take the derivative, I get the same thing because the c just stays there. And by the way, that would allow me to use 0, wouldn't it? But put in c equals 0 again. It's not a singular solution. It's part of our family. Okay. But now I could give you all sorts of different initial conditions, and we could get different actual solutions based on that initial condition. If I tell you that y of 1 equals 2, what do you get for c? Two over e, because what I end up with, 2 equals c e to the first, which is the same as just e. So c is 2 over e, which means I get the equation y equals 2 over e to the x. I can simplify that just a little algebraically. I can write that as 2e to the x minus 1. But you know what the graphs of e to the x look like, right? Let's graph e to the x. Out come the graphing calculators. Actually, the one that's going this way. This one? That's the logarithm, the inverse of it. So e to the x looks like this. Wait a minute, I multiply by a number, it just gets taller, right? Multiply by a negative number, it'll go down instead, but it'll still be looking like 0 over here. So really, I have lots of different choices for graphs that look like something times e to the x. The one I picked at 1 should be up here around 2, should be fairly close to this one. If I gave you 0, 3 as a point, well, then you're nailing down this one. If I give you 1, -2, you're nailing down this one. You can pick which curve you want by adding an initial condition. That is on page 16 in our text. An important sentence. Something I did not mention anywhere in this problem yet, but is really hiding in it, is the interval. What's the interval where this works? What's the domain of this function? Minus infinity to infinity, right? E to the x works for every number. So this is just a constant times this is defined everywhere. As a matter of fact, we go back and look at our graph, it goes all the way to the left, all the way to the right. That's defined absolutely everywhere. So in hiding in this, the interval for this solution is all real numbers. By the way, I will often use that same symbol we used in discrete all those years ago, that funky looking R. But sometimes our choice of initial condition changes our interval. So here is an unfortunately substantially uglier differential equation. And I'm just going to tell you the solution that I like for this one looks like this. Here's an initial condition. Find the particular solution. So with that in mind, my solution is 1 over x squared minus 1. Houston, we have a problem. I want you to graph that for me. And, aha, when I say that my solution should have an interval on which it works, means I can't hit x equals 1. I can't hit x equals -1. So that means in this case, I have 3 different interval choices. I could be over here where my function is perfectly well defined, x less than -1. I could be over here on the right, x bigger than +1. I could be in the middle between -1 and 1, but I can't cross the asymptotes. Which interval should I be using? You may be like, how the should I know? We made a deliberate choice when we chose our initial condition. The interval we choose must contain that x value. So the only interval here available to us that contains that x value is the one that goes from -1 to 1. And that's the solution to the initial value problem. It doesn't just satisfy the differential equation itself, it also satisfies our initial value and has an interval that contains our initial value. Page 16, I think it's example 3 also does this as well. Questions? Again, I can ask how much of Cal 2 you remember, because we did do solving some of these things back then. Chapter 9, section 3, problem number 20. I literally wrote down the page and problem number out of the old calc book. So it's been a while, but we did this one. When I actually work out the solution, which I'm going to put off for the moment, but if you want to, you can go back into chapter 9 of the calc book and go look it up. We get this. Do me a favor, solve for C. Tell me what you get. What's C? 0. So really, this should be ln y minus 1 equals x squared. If I graph that, that should go through the point 0, 2. Can you graph that for me? Cody, you're about to run into a very big problem. Problem as soon as I start to go to the calculator to graph this. There is, but it's hiding. Absolute value you either get by hitting the math option and go to number. There's ABS right there. Or you hit second and 0 where the catalog is, and the absolute value is the very first thing listed in the catalog of things this calculator will do. But my bigger problem is where you're going to graph this. You're going to go graph this somewhere, right? What do you hit to go graph? Graph. Now what? I got to put the equation in. Where do I put the equation? How do I get the ln on that other side? I can't do that. The calculator won't let me graph this implicitly. That's the problem. This is an implicit equation. If I want to graph this, I need to write it y equals. Which means I got to get rid of the ln's. What do I do? How do you get rid of an ln? That is a logarithm. How do I get rid of a logarithm? I need the e in there, right? So I'll exponentiate both sides and I'll get absolute value y minus 1 equals e to the x squared. But I know that e to the x squared is always positive. E to a power is always a positive number. So I don't need the absolute value anymore. And then I move the 1 over. And then I can actually graph that. Yay! I can do it. Like I said yesterday, an explicit solution isn't required, but there are places where it certainly is useful. Now I can graph this, right? I'm going to cheat, and I'm going to tell you that the Mac grapher built into the MacBook does allow you to graph exponential implicit equations. Let me open up the grapher, and then I will go here and I will share this so that it will be captured in the recording. Here we go. You get out of my way. So up there, you'll notice at the top it says y equals. But if I delete that, I can actually get rid of that and I can type in any function I want. Now I've typed in ln of y minus 1 equals x squared. Same picture, right? You graph on anything. I like using the Mac grapher because it allows me to graph implicit equations. I don't have to rewrite and solve for y equals. Places where it's useful. Now that I have this technology, I can avoid that if I want. Click. Stop share. There we go. Presto. So this app called Quick Graph on my iPad. Turn off that so we can see better. Focus. Maybe. Maybe not. That one. Quick Graph. It's $1. It allows you to graph implicit equations as well. You'll notice over there I have the explicit version at the top, the implicit version at the bottom. I don't know why the hell this thing is out of focus. It hates my iPad because that's in focus. So lots of different ways. You can use the Desmos grapher. It'll let you do implicit equations. You've got lots of options for that. Questions? I'm blowing you all out of the water here. Either that or you're like, well, no, sure. So a couple of questions. Can we do this all the time? Even if we're only dealing with a first order differential equation, then I'd want to know, does it go through the point x0, y0? If I had a second order, it'd be x0, y0, y prime 0. Because again, I'd have multiple initial conditions. So even if I'm just looking at first order, can I solve the problem? Does it go through the point I'm looking for? And second, is that solution unique? It turns out that the answer is not always. Sometimes I will get multiple solutions that exist, so it's not unique. Sometimes I won't get a solution at all. I'll give you an initial condition that we literally cannot make work. But it turns out, I mean, here's a nice example. Y prime equals x root y. Remember that one? So we had a solution for this. What was the solution we wrote earlier today? Right? For this equation, we wrote down this solution. And if I give you C equals 0, what's our solution for C? It's the value of C that works there. Which means when we use 0, we have the solution 1/4 x squared, quantity squared, or 1/16 x to the fourth. That's a solution. But I know it's not unique because we already said that it's also possible just to use the equation y equals 0. So there are two different solutions that both work and both go through the point 0, 0. So I found a solution, but it's not unique. That's not nice. This one's tight. It turns out, at least for first order, we can prove a solution exists and is unique using Calc 3. Let's think about a rectangle. From A to B in the X direction, from C to D in the Y direction. And our point X0, Y0 is inside this rectangle somewhere. I don't know where, doesn't matter, it's just inside the rectangle. I suppose I do care because it can't be on the edge. It's got to be inside the rectangle. So in its interior means it can't be on the edge. If there exists, remember that backwards E symbol from discrete? There exists. Oh, sorry, that's part of the conclusion. I skipped a line in my notes. If both f of xy and the partial derivative of f with respect to y are continuous on our rectangle, then there exists, I jumped a line, an interval I with x0 as its center, inside the rectangle, and a unique function y of x on that interval, so that our function y is a unique solution to our differential equation with our initial condition. So notice what I need to have happening here. In order to be able to guarantee a unique solution, I need the expression in my differential equation to be continuous. And I need its derivative to be continuous. We just did an example where we had no unique solution. We had two solutions, right? Let's go back and look at that one again. I'm going to slide back up here for a second. I promise I'll slide back down. This is the equation I want to look at. We had two solutions right here. So let's go back to that example for a second. Our initial condition was y of 0 equals 0, right? For that problem, we had y of 0 equals 0. This is our f of xy. Is that continuous when x and y are 0? It was a long time ago that we talked about continuity. How do you know if that function is continuous? It's what happens over the summer. Too many margaritas, your brains, they got your ears. X is polynomial. It's continuous everywhere. Square root's good as long as y is not less than 0. So that's perfectly fine, right? but only from 0 to the right. Yes? When I multiply those two together, that's perfectly fine, but only from 0 to the right. I'm looking at the point where x is 0 and y is 0. Doesn't that put that point on the edge of my rectangle? Because I want y to be bigger than 0, but I'm looking at y equals 0. That's right on the edge of my rectangle. This failed my hypothesis. The point needs to be inside the rectangle. And this point is on the edge of the rectangle where this works. That's why we ended up with two solutions. It's not in the middle. When it's in the middle, we end up with a nicer picture. Top of page 18, we have this picture. Notice the point x0, y0 is right in the middle of the interval, right in the middle of my rectangle. Oh, well then, here's the point we want to go through. We have some function relating x and y and its slope. We end up with some curve. Now, it may not go all the way to the left and right of A and B. It may not go all the way to the top and bottom of C and D. It's got to go at least a little bit in here. There is a proof of this in the text. I think proving this is a nauseatingly tedious idea, and I don't want to do it. And that's something you'll hear me say frequently in this course, because as much as I like doing proofs in general, because I'm a sick like that, I know it's not really what we're after here. I know we can make this work. Even if we go back to our first example, right? Y prime equals y. Well, in this case, that f of xy part, that's this. Is that continuous? No, it's just a polynomial. Y is polynomial continuous everywhere. What's the derivative of that? Partial of f with respect to y. The derivative of y is 1. And 1 is a constant. It's continuous everywhere. So both of these pieces, the function of x and y and its derivative with respect to y, are continuous everywhere. That means for any point x0, y0 you give me, it'll be inside the rectangle that goes from minus infinity to infinity and minus infinity to infinity. Every point has a unique solution that goes through it. No matter what initial condition you give me, there will be some function that goes through it. As a matter of fact, since I know the solution to this equation looks like that, all I have to do is plug in the x and y and solve for the c. And it will work every time. As a matter of fact, all of the problems we did in Calc 2, in Chapter 9, where we talked about differential equations, had this property. They had solutions. Those solutions were unique, and they were all able to be found in this fashion. Mia, this really gets at that question you asked me before the start of class. The function we are trying to find, the solution function we want, really has 3 kinds of domains. Like our first example, we had 1 over x squared minus 1, right? And Jalen, you pointed out that doesn't exist at 1, it doesn't exist at -1. That's the domain as a function. That's our algebra domain. Hey, this function lives everywhere except these 2 dots. Then we can look at the interval where, sorry, the domain where our function is a solution to our differential equation. And then we can say the interval where we go through the point in question. And so really we have 3 different things. Matter of fact, let me go back and name these 3 things. I'm going to call this first one, I'm going to call this D sub phi. Well, that makes sense. That's the domain. The domain of the function in algebra terms. And then I'm going to say the domain where it's a solution to our differential equation. Let's call that one I. And then the interval where we solve for the initial value problem. The initial value problem was x0, y0, right? We had our initial condition. So we'll call that I0. We had the 1 over x squared minus 1, but then we gave the initial condition at x equals 0. So we could only use from -1 to 1. Could use the part less than 1, -1, bigger than 1. We could only use the part in the middle. It turns out that is always true. So the domain of the function in algebra terms is the biggest possible place the function could exist. That's all the way. In our e to the x case, that was -infinity to infinity. Where is it a solution to our differential equation? Well, maybe it's all of the same places. Maybe it's only some of them. Remember, we had functions, we could have multiple pieces. And then where does it match our initial condition? That's the smallest piece. That's the one we're looking for. This is very much in line with the answer to question 18. Questions? Actually, let me use this one. Instead of -4.9, I'll use -32. This is a second order differential equation with a set of initial values, right? So I'd like to solve it. Advantage. All I have to do to solve this problem is integrate twice. And at each point, once I integrate, I can use part of my initial conditions to solve for the constants that I end up with. So if I know that S double prime is -32, what's S prime? Say again? Almost. I shaded the letter. You're just spelling T as X, that's fine. Okay, but this plus C can be solved for explicitly right here. I know that S prime of 0 is 40. So I know that C is 40. And now I have S prime of T is minus 32T plus 40. And now I can solve for S. What's S of T? Well, but I got to go a step further. I'm integrating here, right? Right. I have to remember that C is a constant. And then when I integrate, I got to put the T on that. But now I know the other part of my initial condition can get used here. 432 is equal to minus 16 0 squared plus 40 times 0 plus D. So D is 432. And I explicitly now have the solution to my initial value problem. I'm pretty sure I've written down all the numbers correctly. I am at the top of a 432-foot cliff. I throw a ball upwards at 40 feet per second, and gravity pulls down at 32 feet per second squared. So this is a physics problem. That's pretty bald.
No, you make classes a little bit.
A little bit. Okay, this is an initial value problem because up there, both of those were given at the same t value with 0. But I could ask in this same scenario, I could ask this. I've just changed the ground rules. This is not an initial value problem anymore. Because those are different t values, this is now called something different. This is called a boundary value problem, and these are called boundary conditions. So in spite of the fact that I still have two initial conditions, which is good because I'm going to need to solve for two different parameters in my solution family, the fact that they're not the same x value or t value means that this is now a substantially different problem. And here, Noah, what you did is actually just as important now because I have to go all the way to S before I solve for either C or D. Because I don't have anything about S prime. So I won't be able to solve like I did up there for the value C equals 40. I won't be able to do that here. But the same process still applies. Why are these conditions different? What does it mean for these conditions to be different than that one? What does the value of S prime of 0 mean in that problem? This one up here. I did say this was a physics problem. What does that represent? Velocity. I don't have any velocities here. What do I have? I have the position at two different times. I know this object at time 0 was a height of 432. And 2 seconds later, it was also at a height of 432. Went up and it came back down. I don't know anything about speed, do I? But I can use that same information to solve. So instead of actually having initial values, my initial velocity, my initial position, I now have some boundaries for my curve that I'm trying to fit it to. You need as many conditions as you have derivatives. A second order differential equation, two conditions. Whether they're initial value conditions or boundary conditions, doesn't matter. If I want to try and solve, I need as many conditions as I have derivatives. But not all of them work. Remember my conditions about existence and uniqueness. This is second order. Those conditions don't apply. So I don't know, is this even solvable? I'm pretty sure I can do the same damn thing. So I go from S double prime of t. S prime of t is negative 32t plus c. S of t is negative 16t squared plus ct plus d. And now I can start trying to solve for c and d. Given these two, which do you think it's going to be easier to use first? If I use 0, everything except b goes away, right? 432 equals s of 0 equals minus 16 times 0 plus c times 0 plus d. Hey, wait a minute, that means d equals 432, just like last time. But now I can actually solve for c. S of 2 equals 432 equals minus 16 times 2 squared plus c times 2 plus 432. What's c? .432 on the left side of the equation will cancel the 432 I got from D. Negative 4 times 16, that's negative 64 plus 2c. But over, I can see is 32. Ta-da! Again, this actually did work. I threw the ball up. I threw it a little slower this time. It happened to be exactly the same height where I threw it from 2 seconds later. Why do I have these two different kinds of equations? Initial value problems often come from real physical situations we encounter where I know everything at one moment in time. The physics example is a great example. I am standing here, I am going to throw the ball, I know the starting speed, I know the starting height, I'll tell you where it's going to be. I have, okay, physics 1 and lab, right? Y'all did this class, physics 1 and lab. Here's the meter stick, here's the hanging spring with the little weight on it, and you go bouncy, 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 bounce, right? You pull it down, you let it go. You pick it up, you let it go. Remember this lab? I know Dr. Bogdan does it. It's just such fun. You know the spring constant. You know the force exerted. Force is mass times acceleration. Acceleration is a second derivative. That's a position equation. But I know what's happening right at the start. At time 0, I know the amount of force being pushed because I've extended or compressed the spring. I know the spring resistance. I got all of the stuff I can work on. We'll actually do some of those examples. But that's a vibration, right? Give me an example of something else that vibrates other than that stupid weight on the end of a spring.
Life.
I get real life and physics. I hate to break you, but I've been doing them both today. A bridge. A bridge is a perfect example. On Route 30, if you go into Pittsburgh on Route 30, when you're in North Versailles, you cross the George Westinghouse Bridge right after the Walmart and the North Versailles bowling alley. And if you look off to one side, you've got the U.S. Steel plant, the Coke Works down in I think technically that's in Edgewood or I think that's the Swiss Fan. But you got this bridge. There's a sign on the side of the bridge. Do you know what that sign says? Marchers break cadence.
Oh, say marchers.
What's it mean?
Make base throughout the entire
If everybody's stepping in rhythm, they'll add the energy of their steps to the vibration of the bridge. The bridge is pinned at both ends. Let's imagine it's a number line. Then one end is x equals 0, the other end is x equals 2. Those pieces can't move, but the rest of the bridge could flex. Those end positions can't move. That's my boundary condition. It's the boundary of the bridge. It is literally true that if you march in rhythm, you could be marching at just the right pace to increase the vibration of the bridge. We'll talk about what that resonant energy is a little later.
Is that with all bridges? Is that just that?
It happens to be bridges that are end pinned. So things like the Fort Pitt Bridge, where you've got it anchored at the wall going into the tunnel, and you've got it anchored on the North Shore, on the point.
Yeah.
And you've also got it anchored, there's another piece that's anchored on the outbound of Monroeville, right? So yeah, all of those end pinned bridges have that sort of vibration behavior. As a matter of fact, out in California, Highway 880. Highway 880 was a double stacked highway, just like the Fort Pitt Tunnel, right? One road on top of the other. Well, it was pinned about every half mile. It was built in sections, right? Well, they had an earthquake. What happened? The two sections collapsed, one on top of the other. Well, that makes sense. It was an earthquake, right? But there's another bridge in Seattle called the Tacoma Narrows Bridge. The Tacoma Narrows Bridge was a suspension bridge. It was pinned at both ends, and it had those pillars in the middle that everything was hanging from. But the ends were pinned. Those two spots were pinned. And they happened to put the pins at just the right places. So it was a third of the length, a third of the length, and a third of the length. When the wind blew through, the vibration of the wind caused the bridge to start to rock in 3 distinct pieces. The bridge is known by the name Galloping Gertie. I wish I was making this up.
So like the first section, the first third, like on the rhythm, like that doesn't mean the middle section, like 5 feet, the other third, and like 6 feet.
It actually was the major third harmonic. The wind was blowing through at exactly the resonant frequency of the bridge, and the major third harmonic was causing the bridge surface to shift. Here's the picture. You can see the bridge twisting. You can see the bump in the middle of the bridge there. You can see the damn thing ripped itself apart. They've got video recorded on the news in 1940. Trust me, go look this sucker up. Break cadence. over a bridge. A bridge is a perfect example of a boundary value problem. Somebody screwed up. I want to be able to solve them in advance. We'll talk about resonant frequency. We'll talk about beat frequency. It shows up in music a lot. But really it's an engineering piece because from a mechanical standpoint, that's all resonance is. That's all that spring behavior is. It's really the same thing that shows up in music. We're just using it as a physical resonance rather than an auditory resonance. Okay. That ends section 1-2. Tomorrow, it's question and answer day, because these two sections, the homework is due on Friday. Make sure you've got your book. I will see you all tomorrow. Bring me lots of questions. The floor will be yours. I'll see you back over in Boyle then.